All right, what's going on, everybody? Today we're doing another LeetCode video. This problem's called find minimum in rotated sorted array. It's a medium, so let's get into it. We're given an array of length n sorted in ascending order, but it's rotated between 1 and n times. So for example, the sorted array nums equals 0 through 7 might become this rotated sorted array. So we see the beginning got shifted 4 times over here, and then the rest of the array just loops back at the beginning. So it can be rotated between 1 and n times. So it is possible that it is not rotated at all, because n times is like equivalent to just not being rotated at all. So notice that rotating an array 1 times results in the array. Yeah, okay. So given the sorted rotated array nums of unique elements, they want us to return the minimum element of the array. So we're given an array like that, like we just described, sorted between 1 and n times, or rotated between 1 and n times. They want us to return the minimum element. We know there's going to be unique elements, and our algorithm has to run in big O of log n time. So basically, they're going to want us to basically write a modified binary search for this problem to get that big O of log n time complexity. So, I mean, all of the examples are pretty straightforward in the sense that they're literally just looking for the minimum. So the minimum of this rotated sorted array is 1, the output there is 1, 0 here, 0, etc. So I'll step through pseudocode for an example here, and then I'll get into the code. So let's take this example. So say we have this array. And before I get into that, actually, let me just make a note here. So the optimal approach for solving this problem is going to be to use a modified binary search for big O of log n time. And then obviously that the space is going to be constant. So I'll just make a note of that also. O of 1 space. So basically what we're going to do here for our algorithm is we're going to have a left pointer. So I'll just keep track of these like this. So we'll have a left pointer, and I'll just call that the full name. So left pointer, we're going to have a right pointer, and this is going to be very similar to regular binary search, so that it's good to know that before trying to get into this problem. So anyways, yeah, we have the left pointer, the right pointer. We're gonna have a midpoint, and let's see, we're also gonna have a result. I'll just call it min. So at first, and I'm gonna make another line down here because it'll help me with these pointers, so I can actually just like mark them. So this is gonna be our left pointer and our right pointer to start. Let's just mark those indices. So this will be 0. This will be let's see, right pointer is going to be 0, 1, 2, 3, 4, 5, 6. So that'll be at index 6. Our midpoint is just going to be, it's always just the average of the left and the right pointers. I find that calculation to be easier than others. So we would just take 0 plus 6 divided by 2, and that would give us the midpoint. So 3, and then the minimum, we're going to update that separately here based on some conditions. So basically, the first condition, we kind of have an edge case. So if the right pointer is at any point greater than the left pointer, we can just return basically, well, we definitely want to at least check if the value at the left pointer is the minimum value we've seen so far and try to update the answer. Because if the right value is greater than the left pointer, we know this whole portion is sorted. That's just like a property of rotated sorted array. So if the right pointer is greater than the left pointer, you know that whole range is sorted, and then you can try to get that left element. Set that to be the answer. So that's one kind of edge case. The real properties for searching are going to be basically if the value of the midpoint is greater than the value at the left pointer, we know that portion of the array would be sorted. So like imagine M was, right here between these. If this value is greater than this one, we know this portion of the array is sorted. Well, what does that mean? Well, we're going to check the edge case where right is greater than left first. So if right's not greater than left, but this point is greater than the left one, we know we need to look over here, right? Because the pivot, so to speak, the pivot, by the way, is like where the array goes from the end to the beginning. So, but regardless, if this value is greater than this one, we know to search this way. Otherwise, we will search the other direction because we know the pivot's going to happen on the other side of the array if this value is smaller than this one. So this is basically the condition here for the search algorithm. So if we go through this, let's just try to walk through it. So basically, so our midpoint is going to be 3 here. So 0, 1, 2, 3. And then we're going to check, okay, is the value of the midpoint greater than or equal to the value at the left pointer, because the right pointer is not. And let me just write that other case. So check if nums right greater than nums left. Because we need to do that first. So, but regardless, so this is not true for the first iteration. This is going to be true. So we're basically going to search to the right. So we'll update our left pointer to be basically 1 plus the midpoint. So that's going to be our new left pointer. And then we can recalculate our midpoint. So, and all of these. So left pointer is going to be at, let's see, 0, 1, 2, 3, 4. The right pointer will be still at 6. And the midpoint is now going to be 5. And, and our min value, I didn't update that before. That would have been, we would have tried to set the left pointer to the mid value. So that would have been 4. And then we would have set the midpoint to the mid value, and that was 7. So the min so far will be 4. So now our mid pointer is going to be there, and we're basically going to check, okay, is the number on the right greater than the number on the left? Yes, it is. So we can take the minimum of the left value. And at that point, when this line of code gets executed, we break from our while loop. So the minimum will get updated to 0 in that case. We break from the while loop and we would just return 0, and we would have found the minimum at that point. Obviously the minimum is 0, so we know that's going to be correct there. So that's basically a walkthrough of the algorithm. Now I'll write the code for that. So we're going to have a left pointer. We're going to have a right pointer, just like we outlined. That's going to be pointing to the last index at first. So the size of that nums array -1. And then we're also going to have a midpoint. So I'm not going to define anything for that yet. and I'm not going to initialize it with the value yet. Just declaring it. I like to declare all my variables outside of the loop, so we don't have to reallocate at all while the loop's iterating. So we have the midpoint. We also need the result variable. And at first, we can pretty much assume we're going to get an answer, but I think it's safe to set this to something first. So I'm going to set it to the just first index, the element at the first index of the array. So num's left. And what we can do here, so now we're going to do our modified binary search. So typical, while the right pointer is greater than or equal to the left. And then the first thing we're going to want to do is check that condition. So is the right pointer, is the value at that right pointer going to be greater than the value at the left pointer? If it is, we can assume that we don't have to assume, we know for a fact that this from the left pointer to the right pointer, that portion of the array that we're considering is going to be sorted. So we can try to set the min value to, and I just realized this is going to be a disastrous variable name here, so I'm going to change that to res, because we're going to be calling the min function here on whatever the previous minimum result was, and then that num's left value. And also we can just break from the loop. So technically, I mean, I don't even think, well, I think there are some cases where this wouldn't be the answer, so it is important to do the min. Because I was messing with that. But yeah, so we do have to do the min there, even though we're breaking. So that can be kind of deceiving, but the min is necessary. So next we need to basically calculate the new midpoint. So the new midpoint can be calculated with that average formula. So make sure to use parentheses on the addition for that. So right plus left divided by 2. And then we're going to try to update the result again, but because the result could potentially be the midpoint if we are, approaching, if the left and the right pointers are going to be touching each other. And that might not even be the only case where this is useful, but regardless, we want to try to set the result here. So we're going to take the minimum of the result and then the value at the midpoint. And we also want to, now we want to use those conditions we were talking about to adjust the left and the right pointer. So if if the value at the midpoint is greater than or equal to the value at the left pointer, we can assume the pivot is going to happen on the right side of the array. So to search the right side, we're going to set our lower pointer to be equal to the midpoint plus 1. And otherwise, we know the midpoint has to be less than the value at the left pointer at this point in the control path. So we can just search the left side of the array, and to do that we will shift the right pointer downwards to search that lower half. So that's pretty much it for the code. Down here we have to return our result, and that's about it. So let's go ahead and run this. And let's see, what did we do here? Res equals min, nums, I just misspelled the variable name for that array. So yeah, so hopefully this video helped you understand the problem better. If it did, please leave a like and subscribe and do all that stuff. Run it up. So see if we can get 100% here. Come on. There we go. All right, yeah, 100%. So now I can go to sleep tonight happy. All right, peace.